Hello. Okay, there we go. My thing was unplugged. I am not in the best of shape right now. I am very, very sick. Maybe not very sick, but I'm just a little sick. But right now, I don't know. I'm just sort of watching YouTube. And I figured might as well start the stream since, doing something coding related. So, yeah. Just looking at some algorithms for coding interviews. Yeah. And then I'm gonna work on my last project. At least try and get a front end out, which is the AI front end basically. Right? So that should be good. Yeah, other than that, just gonna keep watching
both
this.
the root node and the next node to our visited array. From here, we continue going down this same branch, the bottom, through. As you can see, there is one, so we'll go down to it and add it to
Good.
again, until of where depth first search might be useful is for solving a maze, which is actually where they were originally created for. Starting from the entrance of the maze, we look through each path all the way to the very end to see if it contains the menu. The time complexity for this algorithm is given a notation of O of V plus E, where V represents total nodes, aka vertices, and E represents total branches, aka edges. We'll explore the why behind this a bit more in a video dedicated solely to depth first search. But for now, all you need to know is that the runtime is big O of V plus E. Now, let's move on to DFS's counterpart. Breadth first search, called BFS, instead of going all the way down each branch and backtracking up, we'll look at every node at one level before continuing further down. Let's look at a visual demonstration. As was the case with depth first search, for breadth first search, we will also create a visited array to keep track of what nodes we've already visited. We'll also be creating a neighbors queue, which will add all neighbors of a node to. To begin with BFS, we start at the root node, add it to the visited array, and we'll add all of the nodes it's connected to the neighbors queue. We'll then take a look at the first node in the neighbors queue, mark it as visited, and add all of its direct neighbors to the end of the queue. This process continues, and as you can see, we'll have visited each node on the first level before we progress down to the next level of nodes. One real-life example of where breadth first search is used is for chess algorithms. For those of you who don't know what this is, it's where a computer program predicts what the next best move is for any given point in a game. The way they work is by starting at a certain player's turn and taking a look at each possible move they have next. The algorithm looks at all possible moves for the next turn, and then looks at all possible moves from all of those possible moves. As I'm hoping you can start to see, this is just depth first search, where the nodes are moves and the levels are turns. Just like with depth first search, the runtime for this algorithm is also O of V plus E. Again, this will be covered more in depth in a dedicated video to breadth first search, but we'll save that for another day. If you're enjoying this video, 12 to 20 me to know. Sorting algorithms are used to sort lists of elements, usually in ascending order. There are tons of different types of sorting algorithms, but today we're looking at the three most important for interviews. Insertion sort is the first of the sorting algorithms and the easiest to start with. Insertion sort works as follows. The algorithm looks at the first element in the list and compares it with the second. If the second is less than the first, swap the two. Then, compare the element in the second position with the element in the third position. If the third element is less than the second element, swap the two. If this element is also smaller than the first element, swap them again. As you can see, we'll continue with this pattern until we reach the end, and voila, we have a sorted list of elements now. Insertion sort is a simple sorting algorithm, and that's where its limitations are. Insertion sort has a best case runtime of O of n, and a worst case runtime of O of n squared.
It's good.
It is O of n when everything is already sorted, as it only goes through each element, and O of n squared when nothing is sorted, because it has to go through every element times the total number of elements. As a result, insertion sort is best used for lists that are already mostly sorted, or for lists of smaller sizes. Once the lists grow larger and more unordered, the O of n squared runtime starts to become problematic. Now, let's take a look at a sorting algorithm that might be better for large lists. Merge sort is a sorting algorithm that falls under the category of divide and conquer algorithms because it breaks up the problem into Well, if you watch my video as per and we continue to split each subarray in half until the array has been split into pairs. Then, at the same time, each pair is going to do a comparison of the first element and the second element and swap them if the second is greater than the first. Now we have sorted pairs. The next thing our algorithm is sorting the numbers for each group of 4. This process continues all the way back up until we reach the full array, which is now sorted. Merge sort has a Comparing that to insertion sort, we can sort of sorted lists, log n, lists, insertion of n log n, making sense so together. Quicksort is our final sorting algorithm and the most complicated of the 3. However, once you understand how the other 2 work, it becomes a lot easier, which is why I left it for last. Like merge sort, quicksort is a divide and conquer algorithm and is recursive. The idea is to pick a pivot number, ideally as close to the median of the list as possible, and split the list into 2 lists, one where all the numbers are less than the pivot and one where all the numbers are greater than the pivot. We continue this process on each sublist until we've reached our sorted list. Let's look at the visualization for it. We start with our list and try to pick a number close to the median. Once we've selected that number, we move it to the end of the list. Now, we place a pointer at the leftmost element and the rightmost element, and we compare the 2. If the leftmost element is greater than the pivot, and the rightmost element is less than the pivot, we swap them. Otherwise, we leave them as is. We continue through the list until our pointers cross. Once they do, we replace the element at the left pointer with our pivot. Now, everything before our pivot is less than the pivot, and everything after our pivot is greater. We will do the same process on both of these lists now, choosing a median pivot for both and sorting the same way. Once we finish, the list is completely sorted. Quicksort has a best case runtime of O of n log n, but a worst case runtime of O of n squared. You might be wondering why we would ever use this algorithm, as it has a worse time complexity than both of our previous sorting algorithms. Well, this is where it gets interesting and a little bit complicated. Quicksort, when implemented correctly, is actually the fastest of the 3 on average. The complexities behind it are better saved for another video, but for a simple reason, the code in the inner loop of the quicksort algorithm can be optimized to significantly reduce probability of worst case, and is on average 2 to 3 times faster than merge sort.
Jeez.
On top of all of that, quicksort has a space complexity of O of log n, whereas merge sort has a space complexity of O of n, so quicksort is a bit better for the memory. However, one of the largest drawbacks to quicksort is that all of this relies on the code being optimized. Any little mistake or inefficiency in the quicksort code can cause the algorithm to run much slower, and it is a much harder algorithm to implement than merge sort. That wraps up our sorting algorithms. Before this video ends, I want to take a look at one more type.
Greedy.
When you think of someone being greedy, what do you think of? Usually, it's someone who always wants and does what the best thing for themselves is in any scenario. Well, that's exactly what this algorithm does. Greedy algorithms are algorithms that make the best possible choice at every local decision point. Put more simply, every time they have to make a decision, They just look at what the next best move is without looking too much into the future. We're first going to look at when not to use greedy algorithms, and then when you should use them. Greedy algorithms are not used for efficiency, because typically, they're not looking at every possible outcome, just the best outcome at each stage. Here's an example of where a greedy algorithm doesn't work optimally. Consider this scenario. For each decision you make here, you have to spend a certain amount of money indicated by the number on the path. Think for a moment, what should you do? Hopefully you came up with this path as the correct solution. However, using a greedy algorithm, we might not get this. The algorithm first looks at the first two choices, 7 and 8. It chooses what's best right then, which is a 7, and moves on. From here, it looks at its next two choices, 9 and 10. Again, it chooses what's best in the moment, which is a 9, and reaches the end. The algorithm reached the end spending $16 total. But if we did it ourselves, we could reach the end spending $3 only. So why ever use them if they're inefficient? Well, for a scenario like the one above, we could have easily developed a DFS or BFS algorithm to find the optimal solution. That's because the problem is simple enough for a computer to solve it that way. In fact, we could even brute force it and have the computer calculate every possible outcome. But what happens when we have impossibly large amounts of outcomes to go through? Sometimes, even modern day computing can't go through every single scenario to get the optimal answer. This is where greedy algorithms are used. If you can't get the exact right answer using an optimized algorithm, it's best to use a greedy algorithm and get something that's relatively close, even if not 100% accurate. One of the most famous examples of this is called the traveling salesman problem. This problem provides a list of cities and distances between each city and asks for the shortest possible route that visits each city once and returns to the origin city. The formula for total possible routes is n-1 factorial divided by 2. If our salesman wanted to visit 5 cities, that gives us 12 possible routes. If our salesman wanted to visit twice the amount of cities, 10 cities, that gives us 181,440 possible routes. Just doubling our city number gives us an exponential growth in route possibilities. But still, 181,440 routes can be solved by a computer in mere milliseconds. Now, let's consider that the traveling salesman wants to visit every capital city in every US state. As there are 50 US states, that gives us 50 total cities. Take a guess as to what the possible route count is. A few million? Maybe into the billions or trillions? Well, if you guessed anywhere near there, you're not even close, because the total number of routes is this. Yeah. And while a supercomputer might be able to calculate that one day, that's only 50 cities. Just for fun, let's say it was 1,000 cities. Ready for the number? As you can see, we definitely won't be finding the exact optimal route from every possible route. Here's where our friend the greedy algorithm comes in. Let's choose an arbitrary starting city and write a simple algorithm that always chooses the next city that's the least far away. We can continue this process until we reach the end, and then return to our starting city. This is definitely not the most efficient way to do it, but as we've seen, we can't calculate the most efficient solution, and we'll still get an answer that is far more efficient than randomly choosing cities. So, to summarize all of that, greedy algorithms are used when finding the optimal solution might not be possible, so we want something that's relatively accurate. Those are the 7 most important algorithms for interview.
Nytta kan det vara actually. where my days go, Jesus. Hello. Hi. On a break. How's the weather? I'm kind of dying right now. 23 degrees. I'm opening my window. It's too damn hot in my room. Oh my days. It's empty, right? Absolutely no idea. What? How do I use prawn, man? I don't know. Cron is now Notion calendar. Sick. Ah, my nose getting me good. Let's try something. Oops, I don't. Oh. Situation topic. I have no idea what that means, by the way. I don't know what I wrote. Missing was fantastic. Oh god. Oh good god. Oh, I can't work. I'm dying. I get sick 2 times in this thing. I swear I got sick like twice. Nah, I gotta take better care of myself. Jesus. Might just call it a fucking day, honestly. Got one more day, you know. Probably spend most of it doing this. Early wake up. It's done, and then yeah, worry about everything else later. And then sure, everything I've done. Call it a successful 30 days, you know.